Today I'll be doing Codeforces round 624. Oh, I see. prefix sums. What? Oh, the final try, okay. Looks about right. What? Oh. Yeah, I thought it was an integer array, but it was long, so the bounds were incorrect. Which problems are people solving? D and F. you just generate all the triples that satisfy this. Go through all of them and then see. Yeah, I just hope that the generation will be fast enough. It seems like it is because my computer is slightly slower, so I think it should work on Codeforces. Let's see what people are solving. D and F. So I should look at F first. Slept it. Okay, it's probably fast enough. X is the It's funny how it took less time to solve D than B or C. So let's plot the x-coordinate in terms of time. So if one line looks like this, then for lines with smaller slope, okay, let's just consider the lines behind. So with lines with bigger slope, then with smaller slope, then it won't intersect out, so it's just this. Otherwise, it'll be 0 at some point if the slope is smaller. Okay, so let's sort everything by x first. All x are distinct, okay. Then we'll process them in order. And then for slopes which are greater, want to do this. Okay, so I guess I have to sort all of the slopes first. Is equal to go from top to bottom and then okay. And the second one will be the x coordinate. Wait. Then I find those with a smaller slope. Yeah, okay, that seems right. And then multiplied by the current x coordinate minus this. Okay, now I just need to implement my binary index tree. Three, 13, oh no. Is there something that I missed? On smaller slope with smaller coordinate. Probably forgot the same slopes. So if the slope is the same, then it should still be counted. Okay, good. Should be good. One, two, three, 1, 2. So this is 7. Okay, so I'm almost 5,000. Let's just try small cases. So if I want 1, it's this. Can d be equal to 0? No. Okay. If I want 2, it's this. Oh wait, might be, you're given n as well. Okay, so what you do is you start like this, I guess, and then you continuously move the last vertex upwards. So how do I implement this? Figment. This is a bit complicated. Test 23. I think it'll pass. If it passes, then oh cool. And I'm first. At least for now. I don't think anyone can get over me and can beat me unless I get hacked. So anyways, time for the solutions. So for an A, you basically just need to do some casework. So basically you think that it seems that you don't need too many operations in order to get from A to B. So that's why it seems like casework. So the most obvious case is when A is equal to B, and then the answer is 0 in that case. And then what about when the answer is equal to 1? And that means that if B is greater than A, then we can add an odd integer. So if A is smaller than B, then we need to make sure that A and B have different parities. And if A is greater than B, and that means you can only subtract an even integer. So if A is greater than B, then we check that A and B have the same parity. And it turns out that if all these 3 cases are not true, then the answer is 2. And that's because if the only cases left are if A is smaller than B and B has the same parity as A. So in that case, you can add 2 odd integers to make an even integer. And then there's the other case, if we want to subtract an odd integer, then what we can do first is we can add 1 first and then subtract an even integer. Then that'll basically subtract an odd integer from A into B. So for B, so notice that if you have, let's say in P, if the positions are 1 and 3, so in our array looks like, maybe it looks like this. So that means you can switch these 2 pairs. And these 2 pairs basically don't intersect with each other, so we can consider these 2 pairs independently, and it's pretty obvious that we should, within each pair, we should sort the pair, so in order to obtain the best result. So after we sort, we'll get 1, 3, 2, 4, and we find that it's impossible. But what if the pairs are adjacent to each other? So maybe we have P is equal to 1, 2, 3, and 5. And then we have our array will be 1, 5, 4, 3, 2, 6. That means you can switch these pairs. And notice that these 3 pairs, they intersect with each other, but then this pair is on its own, so we can consider it separately. And notice that switching adjacent pairs, that's basically what bubble sort does. So in fact, what we can do is we can sort this entire range here, and then we can sort this range as well. So basically, what we do is, given the array P, we find the continuous ranges formed from the pairs of P. Then we sort them. So after sorting, this becomes this. And then we find that this still isn't sorted, so it's impossible. And for the code, the constraints in B allowed for quadratic solutions to pass, but my code is actually works in n log n. So what I do is, first I sort P, then I start from the first element of P and I find the maximum range of adjacent pairs. And then what I do is I find that range and I sort the range. And then after I process the first range, I move on to, I set I equals to j to move on to start from the next element. Then after I sort all of these ranges, I just check if the array is sorted. And if it's not, then I output no, and otherwise it's yes. For C, basically what we want to calculate is for each index, how many times do we press that index. So for example, in the first sample case here, what we do is the first time we hit this combo, the second time we hit these 3 letters, and the last time we hit all 4 letters. So we find that the first index is we press it 3 times, so all 3 times we press this. And for B and C, we only press it 2 times. And for the last one, we only press it once when we do the final combo. Okay, so what we need to, in order to do this, we'll basically just use prefix sums. So at first, for the last combo, we'll basically just add 1 to the end of the array, and then for each prefix, we basically add 1 to the end of the prefix, and then we go from right to left, and then we do the prefix sums from right to left. So now in this array D, we store how many times the index I will be pressed. And after we have that, we just go through all characters in the array. And then since we have number of times the index I is pressed, we can add that to our count for each letter. And after we process all the characters, we have our counts and we can output them. Okay, so for D, the intuition for this problem is that if you know about the number of pairs A and B such that A is divisible by B, and then both of them are smaller than, both of them are integers from 1 to n, then there are about O of n log n such pairs. So this problem seems similar, but except we have triples. And by the way, if you don't notice, this is pretty standard. Basically, the number of divisors can be it can be approximated by this function. So if I should write, okay, so for a given A, there are about n divided by A multiples of B that we can choose. And then this sum, if you use calculus, it turns out to be this. So that's why it's O of n log n. Then I'm pretty sure that if you have 3 elements, it'll be something like O of n log squared n, or maybe O of n, or maybe something like O of n squared n. But it doesn't matter. Like, if you generate all the triples such that this is true, you find that it runs pretty fast. This is what I do here. So basically, I iterate over A, and then I iterate over B. And then B must be a multiple of A, so I start from A and then I add A each time. And then C must be a multiple of B, so I start from B and I add B each time. And I push, and I just add the triple to the vector. And then for each test case, I just go over each triple, and then I test the triple. So I just add up the absolute differences in order to get the number of operations I need. And then once I find the best answer, I just output it. So this is pretty straightforward. Okay, and I'm moving on to F first because F is, in my opinion, F is definitely easier than E. Okay, so for F, basically what we can do is we can plot each, let's plot each point on the plane. So y of t will be equal to xi plus t times v of I. So we get, and let's fix some line. Might look like this, and then let's just assume that we only want to count the lines which are lower than it. So maybe which start lower than it. So for example, like these lines, and we want to count the intersection of this line with all the lines which start below it. So we can notice a very simple rule here. So if the line below it happens to have a slope which is smaller, for example, if it's like this or if it's like this, then the smallest distance will just be the difference of the initial x coordinate. However, if the slope is greater, so if the line looks something like this, then basically we'll have 0 at this point. So what we need to do is we want to count the number of pairs such that xj is smaller than xi and vj is greater than vi. Because vj needs to be wait. Let me just check my code here. Oh no, wait. Vj has to be smaller than or equal to vi. So when it's equal, then it's parallel, so it'll never intersect, and then if it's smaller, then it'll also never intersect. And then out of all of these pairs, we want to find the sum of x of I minus x of j. So what we're going to do first is we'll sort all the points by their x coordinate. So then we'll iterate from small I to bigger I. And then what we do is we put all of the points in a binary index tree. And the binary index tree should be sorted by their velocities. So if we're at a certain I and we want to find, if we want this condition, then we'll just query the binary index tree using, we'll query the binary index tree using this, since the binary index tree gives us range sum queries. So, oh, by the way, the given velocities, they can be big, so what we need to do is we need to get all of the velocities first, and we need to sort them. And then we find for each I the relative position of point I, the relative velocity. And then we need 2 binary index trees. So the first binary index tree stores the number of lines within the number of lines, and then the second binary index tree will store the sum of the x coordinates of the lines. Then using that, how do you get how do you find the sum of this? So in fact, if we find that there are k points which satisfy the condition above, then we can rewrite our sum as k times x of I minus the sum of x of j. And this k over here, we can find it in our first binary index tree. And then, so that's why we add 1. And then this sum over here, we find it in our second binary index tree. And that's why we add the x coordinate to that binary index tree. So I think once you realize the observation about the lines intersecting, then it becomes a pretty standard problem about finding the sum of all the pairs which satisfy some inequalities. Okay. So then, problem E. So first we should consider the minimum and maximum sum of depths we can achieve. So the minimum is hard to think about, but the maximum is actually pretty easy. So the maximum sum of depths, if we have n nodes, it's basically just if we if we arrange them in a line like this, then this will give us the maximum sum of depths, and this will turn out to be, this node will give us +1, this is +2, and this is plus and minus 1. And using the formula for the sum of the first n integers, we find that the sum of depths is equal to this. So basically when we input, if we find that the sum of depths is already greater than this expression, then we know it's impossible. And otherwise, what we can do is we can look at the deepest node, and what we'll do is we'll iteratively decrease the sum of depths by 1. So in our first step, what we'll do is we'll basically just move this up by 1. And then in our second step, we'll move it up by 1. And then we do this until we get to the top, and then we can't move this anymore. And then, okay, so that's basically done. And then so we move on to the next deepest node, and then we move this up by 1. So we get this. And notice that we can't move it up over here because we're given in the problem that we're given the problem that it has to be a binary tree. So each node has at most 2 children, so we can move it at most up here. And then for 3 we realize that we can't move it up anymore for the same reason. So this actually gives the minimum sum of depths for 5 nodes. So we can find that this is 1 plus 1 plus 2 plus 2. So this is 6. So you basically just do that process, and in order to, let's say, so we start out with, I'll go back to my example. So let's consider the sample case. So we start with 5 nodes, and we want a sum of depths of 7. And right now we have a sum of depths of 10. So that means we should try to move the last one up by 3. And then we move it up by 3. And it goes over here. And so now it's 7. And then once we get to 7, once we get to the one we want to input, we just stop. Okay, so about the implementation is a bit more complicated than the idea. So the first thing you need to do is you need to store the number of children for each node. So in the beginning, every node has a children of 1 except for the last node. And then every parent is just set to, the parent of I is just I minus 1. And then this W, this basically stores, W of I will store the nodes which are available at depth I. So what I mean by that is, in here, W of 0 will basically store 1 because we can move this 5 up here to the 1. But after we move the 5 up there to the 1, 1 will not be available anymore. So that means you need to erase the 1 in W of 0. And then we do the same thing for all of the other nodes. So this will be equal to 2 because 2 is available. But then after, when we move 4 up here, then 2 will not be available anymore. So this will become empty. And then, so what we do is we start from the last node. And then first, we set the number of children of U to 0. And then, so we basically just find the first level which contains a node which will work. And then if that level is, so if a plus 1 is equal to u, which means that we can't increase our answer anymore, then we'll just break. And otherwise, we'll look at the number that we still need to decrease, and we'll compare it with the difference of the depth. So if we find that if we find that, so for example, if you have this, and then if we find that we don't actually need to go all the way, maybe we just need to go to the middle over here, then we'll basically just do that, and it's just some math. So we want a difference of s minus d, so subtracting, if we move the parent up higher each time, then it'll subtract the depth by 1. So that's why we do this. And then we set s equal to d, and we just stop this loop. Otherwise, we find one of the vertices that we can move u to. We set the parent of u equal to v, and then we increase the number of children of v. And then since it's a binary tree, if we have 2 children, then we just remove it from the list, so then we won't choose it anymore. And then we decrease the sum, and then we make u available to have children. But then we move on to the next node. Yeah, so that's basically it. I think the implementation for E was, I don't think it was that, I think it would have been better for an educational round and not a Division 3. More people have solved it, but it still looks pretty hard.